Hello, today we'll be doing word search number 2. This is a pretty difficult problem. Involves necessitating a try for us to complete this particular problem. It's like two problems in one. Both backtracking and a try in one problem. So why backtracking? Because we need to find every single word in this particular grid. And that will take us forever if we do this in a, I guess, brute force manner, because we would have to go at each item and we would have to check each particular place for each particular word, and that's just a DFS into infinitum. So we have to go 4 directions. We have to go to the power of the grid, which is m times n. And we have to do this for m times n items, and we have to check every single word, which is taking forever. So what we're gonna do instead is once we've identified that there are no more items that is possible using a try, like there's no O, we can skip it. That's O of 1. If there are more, then we keep going through an entire list of words and then remove the words that we don't need. So what is it limited by then? What it's limited by then is number of let's say m times n. We're gonna do that. It's limited to to check every single try, which is every single word. And do we go forward to the mn? Yes, I think, yeah, we do, but I guess the average time is much faster, and we don't check every single word. So that's the new time complexity. So let's do it. Let's create that try first, and let's create that init. So let's see. Right. So here we go. Definition init self.children equals a dictionary, and self dot is word equals false. So we're gonna have to add the word to our dictionary. So for C in word, if C not in current children, make that happen. And set current equals current children at C. And then lastly, what we need to do is set this particular word to true. One thing we do need to do is remove the word from our list, because we don't want to be going down extra paths. So we have to prune the words. Prune word, self word. How we're gonna do that is a pretty doozy. What that means is that we will have to do a little bit of work. That work is to set up a node and child key. And this is going to be a list of a tuple of a try node and the string. So what this is going to be is the parent to the child key, so that when we have the parent key, we can point to the child key, and we can get that key to see if it has any children. If it does not have any children, we're going to remove it. Because it no longer has any children, we can remove it. And if we keep removing it, then we will remove the entirety of the chain of, I guess, nodes. So what we're going to do first is add the current item and the character. Cur equals cur.children of the char. And let's keep moving. So for parent node and child key in reverse, because we need to remove these items in reverse. So target node is equal to parent node dot children child key. So it goes to the child key, and if it has no children, then we can delete this particular node, child node. Else we're going to return. And that's how we clean up our tree. Alright, so that's the first bit. Now we're going to do our second bit of the code, which is to go through the matrix and search for each single word. So I have a try node. So for W in the words, for word in words, we're going to add each word to our tree. Let's get the rows and columns so that we can go through this properly. And the result and visited equals a set and a set. Perfect. And let's do DFS. Well, actually, we can set this to an array now because, well, we're sure that we're going to get the word once because we delete the word afterwards. So let's define our DFS. We have a row, we have a column, we have a node that we start at, and we have a word that we're going to build towards. And so if this is where the backtracking comes in, if it's less than 0, column is less than 0, or row is equal to rows, or C is equal to columns, or the board of R and at C not in node.children, or the row and column is in visited. Then we return. Otherwise, visited dot add the row and column so we don't visit it again. And next step is we set our node equals to node.children to move it along into the tree. Perfect. Oh, whoops, that's not good. There we go. Nope, not good. Okay, keep going. Also, it's great. So, and we add to the word, length of the word, so we can make sure that we are getting the word. And if node.isWord, if we found the word, we append the word to our list of words. We set the node isWord is equal to false, and we're going to clean up the number of words that just if it exists in our tree. We're going to clean that up so that we don't have to revisit these items next time. And now time to do backtracking. We're going to go through each particular item. So this goes into the 4 directions, and we're going to use the new node where we're at and continue moving on into the next word. So next row and column. Yeah, so perfect. You're wondering, why do we have the word and node? Yeah, the reason is because, well, that way we don't have to like regenerate every single word every single time it's cached. So once we've done with the DFS, let's remove the row and column, and so that we can start anew and go to the next DFS call. So with this, we can do for r in rows, range rows, and for c in range columns. And we're gonna have to do a DFS on each particular row and column. We're gonna set it onto a root, and we have a word which is gonna be empty. And with that, we can return the results. Run the code. Oh, shoot, what happened? Let's see. Yeah, let's do a print statement. Let's see what's going on here. Looks like nothing's happening, so let's print word, run code. Then nothing's printed. So less than 0. Okay, everything looks good here, but that's really odd. So it never prints the word. So that means it always ends here. Let's run. Yeah, that's exactly what's going on. It never enters this particular. So maybe what's going on is that we're not adding the word properly. Let's see. So, I'm sure we added every single word. Let's see what's going on here. Yeah, I think there are. So we have O, P, N, E, and R. And let's print the length. I'm sure we have the words. Yeah, 1, 2, 3, and 4. So, right. That's really odd. I'm gonna check my notes, see what's going on here. It's not reaching this point. So it must be something wrong with this particular part. Yeah, I just went through the whole table once. So it has to be here. But it's not. I don't see it anywhere. Yeah, I don't see the problem. I don't see even the fact that we're pruning the words. So all right, I'm gonna pause it and I'll be back. So how do we do this pausing? Okay, we're back. Sorry for the pause. What happened was that we had a little typo here, this particular point, and we had a comma instead of an or. That led to this statement always being like true. And so yeah, that's what happened. So with that fixed and a couple typos, this ran successfully. I hope you enjoyed the video. Like and subscribe. Want more videos, check the link in the description below. Thank you very much. I'll definitely do this video again next time and get this done better. I'm sure I need more practice on this particular type of problem. Let me give you two shots. First shot of the class try note, and the second shot of the solution. Oh, that means I have to shrink this. Yeah, solution. Thank you very much, and I will see you in the next one.